Welcome! Today, we will dive into LeetCode problem number 403, Frog Jump. This is an exciting dynamic programming challenge where we determine if a frog can successfully hop across a series of stones to reach the last one. Let's explore the problem and break it down step by step. In this problem, we are tasked with helping a frog cross a river by jumping on stones. The stones are laid out in a straight line, and their positions are given in a sorted array called stones. The frog starts at the first stone, which is always at position 0, and the goal is to reach the last stone in the array. The frog has a unique way of jumping. It can jump forward by a distance of k1, k, or k plus 1 units, where k is the size of its previous jump. However, the frog can only land on a stone if that position exists in the array. Initially, the frog's first jump size is 0. The goal is to determine whether the frog can successfully reach the last stone, and the output is a Boolean value, true if it's possible for the frog to cross, or false otherwise. Now, let's look at a concrete example to understand the problem better. Suppose the input array of stones is 0, 1, 3, 5, 6, 8, 12, 17. The output for this case is true, indicating that the frog can successfully cross the river. Here's how the frog can make its jumps. It starts at position 0 and jumps 1 unit to reach position 1. From there, it jumps 2 units to position 3, and then another 2 units to position 5. Next, it jumps 3 units to position 8, followed by a jump of 4 units to position 12. Finally, it makes a jump of 5 units to reach the last stone at position 17. Each jump is valid because the frog lands on a stone that exists in the array, and the distances follow the rule of k1, k, or k plus 1. In contrast, consider another example with the input array 0, 1, 2, 3, 4, 8, 9, 11. This time, the output is false, meaning the frog cannot cross the river. Here's why: the frog can jump to positions 1, 2, 3, and 4, but once it reaches position 4, it gets stuck. The next possible jumps are 3, 4, or 5 units, but none of those positions 7, 8, or 9 are valid based on the stone positions. As a result, the frog cannot progress further or reach the last stone. Let's explore another example where the frog succeeds. For the input array 0, 1, 3, 6, 10, 15, 21, 28, the output is true. Here, the frog can cross the river by making progressively larger jumps. It starts with a jump of 1 unit to position 1, followed by a jump of 2 units to position 3, then 3 units to position 6, and so on. The jump sizes increase sequentially, 4, 5, 6, and finally 7 units to reach the last stone at position 28. This demonstrates how the frog can adapt its jump sizes to match the layout of the stones. Lastly, let's consider a scenario where the frog fails. If the input array is 0, 1, 2, 3, 4, 8, the frog cannot reach the last stone. After jumping to position 4, the frog is unable to make a valid jump to the next stone because the gap between positions 4 and 8 is too large. None of the possible jump sizes, 3, 4, or 5 units, can bridge this gap. This highlights how gaps in the stone layout can prevent the frog from crossing the river successfully. To determine if the frog can successfully reach the last stone in problem number 403, we considered several approaches. The first is a brute force method, which involves simulating every possible jump the frog can make. The intuition here is to recursively explore all paths by attempting jumps of size -1, the same size, or +1 from each stone. While simple to implement, this approach quickly becomes computationally expensive due to its exponential time complexity, 3 to the power of n. This happens because each stone can lead to 3 potential paths, resulting in an explosion of possibilities as the number of stones increases. For example, with a large input size like 10,000 stones, this method becomes impractical. Although conceptually straightforward, the trade-off is clear: brute force sacrifices efficiency for simplicity, making it unsuitable for larger problem constraints. A more effective solution is the dynamic programming approach, which leverages a hash map to optimize the process. Here, the key idea is to track reachable jump sizes for each stone, avoiding redundant computations. Specifically, we use a dictionary, where each key represents a stone, and the value is a set of jump sizes that can land the frog on that stone. Starting with the first stone, the frog begins with no prior jump, so we initialize dp, 0, as a set containing 0. From there, for every stone, we iterate through its reachable jump sizes and calculate the potential next positions by adding the jump size -1, the same size, or +1. If these positions are valid stones, we update their reachable jump sizes in the dictionary. The solution boils down to checking if the last stone has any reachable jump sizes. This approach has a time complexity of n², as we process all jump sizes for each stone, making it efficient for the given constraints. While it requires additional space for the dictionary, this trade-off is justified by the significant reduction in redundant calculations. On the other hand, a greedy approach, which tries to make the longest possible jump at each step, fails because it risks skipping necessary intermediate stones, making it infeasible for this problem. The dynamic programming solution with a hash map is the chosen strategy for this problem because it balances efficiency and scalability. By storing only the reachable jump sizes for each stone, we ensure that every path is explored only once, avoiding unnecessary recomputation. This makes the approach optimal for large inputs. One key observation is that the frog's jump size at any stone is determined entirely by the jump size from the previous stone. Using a hash map allows fast lookups and updates of reachable positions, which keeps the algorithm efficient. The breakthrough here is realizing that we don't need to track all possible states, just the jump sizes that matter for each stone. This significantly reduces the state space and complexity. While the approach does require additional memory to store the dictionary, it achieves an impressive n² time complexity while maintaining a manageable n² space complexity in the worst case. This trade-off makes it a robust solution for the problem while ensuring the algorithm performs well within the constraints. The frog jump problem challenges us to determine if a frog can travel across a series of stones positioned at increasing distances, starting from the first stone and reaching the last stone. The frog's movement is governed by specific rules. It can jump k1, k, or k plus 1 units from its current position, where k is the size of its previous jump. The task is to figure out if the frog can reach the last stone while following these constraints. To solve this efficiently, we use a dynamic programming approach combined with hash sets. The central idea is to track, for each stone, the possible jump sizes that could have landed the frog there. From this information, we can determine if the frog is capable of reaching the final stone. First, we initialize a hash set called stone_positions to store all stone positions for quick lookups. We also maintain a dictionary DP, where the key is a stone and the value is a set of jump sizes that can land the frog on that stone. Initially, we set DP 0 to 0, indicating that the frog starts at the first stone without any prior jumps. Then, we iterate sequentially through the stones, using the stored jump sizes at each stone to simulate potential future movements. For each stone, we use the jump sizes stored in DP to simulate the frog's future jumps. If the current stone has possible jump sizes such as k, the frog can attempt jumps of k1, k, or k plus 1 units. It's important to ignore jumps smaller than 1, as the frog cannot move backward or remain stationary. For each valid jump size, we calculate the potential next stone position as next_stone equals s plus jump_size. If this next stone exists in our stone_positions hash set, we add the jump size to dp, next_stone, to indicate that the frog can now reach that stone with this jump. After processing all stones, we check the last stone in the sequence. If the dictionary DP contains any jump sizes for the last stone, we return true, as this means the frog successfully reached it. Otherwise, we return false, indicating that the frog cannot complete the journey. The key insights here are the use of hash sets for efficient lookups and the bounded nature of the problem, where the total number of states is limited by the product of the number of stones and the maximum jump size. This makes the approach computationally efficient. Additionally, by storing jump sizes for each stone, we avoid redundant calculations for stones we've already processed. The algorithm relies on two primary data structures for efficiency. First, the dictionary DP maps each stone to a set of jump sizes that can land the frog on that stone. This allows us to efficiently keep track of all valid jump sizes for each position. Second, the hash set stone_positions stores all the stone positions, enabling constant time checks to determine if a potential next stone exists. Now let's consider the complexity of the solution. The time complexity is n*k, where n is the number of stones and k is the maximum jump size. This arises from processing each stone and evaluating potential jump sizes. Similarly, the space complexity is O and *k, as we need to store reachable jump sizes for each stone in the dictionary. It's also important to address edge cases. If there's only one stone, the frog is already at its destination, so we return true. If a gap between two consecutive stones exceeds the maximum possible jump size, the frog cannot cross it, and the answer is false. Lastly, unreachable stones, those that cannot be landed on based on the jump constraints, should not interfere with the computation, as they remain empty in the DP dictionary. These considerations help ensure the algorithm handles all scenarios robustly. Let's walk through an example to solidify our understanding. Suppose the input stones are 0, 1, 3, 5, 6, 8, 12, 17. First, we initialize stone positions as 0, 1, 3, 5, 6, 8, 12, 17, and DP as 0, 0, since the frog starts at the first stone with no prior jumps. Then, we process each stone. For stone equals 0, the only jump size is 0. The frog can make a jump of size 1, landing on stone equals 1, so we add 1 to DP, 1. For stone equals 1, the jump sizes are 1, allowing jumps of size 1 and 2. With these, the frog can reach stone equals 3, and we update DP, 3, accordingly. This process continues for all stones. By the time we reach stone equals 17, the dictionary shows DP, 17, equals 4, indicating that the frog can reach the last stone with a jump size of 4. Since the last stone has reachable jump sizes, we return true, confirming that the frog successfully completes the journey. This code solves the problem using dynamic programming with hash sets to track jump sizes at each stone. First, it checks if the second stone is exactly 1 unit away, as this is a mandatory condition for the frog to proceed. If not, the function returns false. Next, a dictionary stone_positions is initialized where each key is a stone's position and its value is a set of possible jump sizes to reach that stone. The jump size to reach the second stone is initialized as 1. The algorithm iterates over each stone and its respective jump sizes. For each jump size, it calculates the possible next stones the frog can reach using steps of jump 1, jump, and jump plus 1. If the calculated position exists in the stone_positions dictionary and the step size is positive, it adds the step to the set corresponding to that stone. Finally, if the set for the last stone is non-empty, it means the frog can reach the last stone, and the function returns true. Otherwise, it returns false. Here, we start by importing the necessary utilities and defining our solution class with the method canCross. The input is an array of integers representing the positions of stones in the river. The first thing we handle is a simple edge case. If the second stone is not at position 1, the frog cannot make the first jump, so we return false immediately. After that, we initialize a map to keep track of the possible jump sizes for each stone. The keys in this map represent the positions of the stones, while the values are sets that store all the jump sizes the frog can use to reach that specific stone. We populate this map with all the stone positions, associating each one with an empty set initially. Next, we handle the first jump explicitly. Since the frog starts at position 0, its first jump to position 1 must be of size 1. So, we add 1 to the set of possible jumps for the stone at position 1. After the setup, we iterate over each stone and explore the jump sizes stored in the map for that stone. For each possible jump size, we attempt 3 new jumps, 1 smaller, 1 equal, and 1 larger than the current jump size. These are represented by jump 1, jump, and jump plus 1. If the resulting jump size is positive and leads to another stone, we add it to the set of possible jump sizes for that target stone in the map. Now, the nested loops ensure that we explore all potential jump sizes for each stone. If a valid step is found, it is added to the possible jump sizes for the target stone. This way, the map dynamically tracks all reachable stones and the jump sizes required to reach them. Finally, we check the set associated with the last stone. If this set is non-empty, it means the frog can reach the last stone by using 1 or more valid sequences of jumps, so we return true. Otherwise, we return false, indicating that the frog cannot reach the end. This implementation efficiently uses the map to simulate all possible paths the frog can take while avoiding unnecessary computations, ensuring that we solve the problem within a reasonable time complexity. Here, we start with a basic success case. The input array of stones is given as 0, 1, 3, 5, 6, 8, 12, 17. The frog begins on stone 0 and can jump to the next stone at 1 with a jump of size 1. To track possible jumps, we initialize stone_positions as a dictionary where each stone maps to an empty set. As the frog jumps to stone 1, we add the jump size of 1 to stone_positions, 1, so it becomes 1. Now, from stone 1, the frog evaluates possible jump sizes, 1-1, 1, and 1 plus 1. Of these, a jump of size 2 successfully lands on stone 3, so we add 2 to stone_positions, 3. Moving to stone 3 with a jump size of 2, the frog considers jumps of 2-1, 2, and 2 plus 1. A jump of size 2 lands on stone 5, and we add 2 to stone_positions, 5. Similarly, a jump of size 3 lands on stone 6, so we add 3 to stone_positions, 6. This process continues for each stone, evaluating valid jumps at each step. Ultimately, when the frog reaches stone 17, stone_positions, 17, contains 4, indicating that the frog can successfully reach the last stone. Therefore, the output is true. Now, let's consider a failure case. The input stones array is 0, 1, 2, 3, 4, 8, 9, 11. The frog starts at stone 0 and can jump to stone 1 with a jump of size 1. We initialize stone_positions to track possible jumps, starting as a dictionary where each stone maps to an empty set. When the frog jumps to stone 1, we add the jump size of 1 to stone_positions, 1, making it 1. From stone 1, the frog evaluates jump sizes of 1-1, 1, and 1 plus 1. A jump of size 1 lands on stone 2, so we add 1 to stone_positions, 2. A jump of size 2 lands on stone 3, and we add 2 to stone_positions, 3. At stone 3, with a jump size of 2, the frog considers jumps of 2-1, 2, and 2 plus 1. A jump of size 1 successfully lands on stone 4, so we add 1 to stone_positions, 4. However, at this point, the gap between stone 4 and stone 8 is too large for any valid jump. The frog cannot proceed further, meaning it is impossible to reach the last stone. As a result, the output is false. Finally, let's analyze an edge case where the input stones array is 0, 2. The frog starts at stone 0, and the second stone is at position 2. For the frog to reach stone 2, it would need to make an initial jump of size 2. However, the first jump is always limited to a size of 1, so the second stone is not reachable. The algorithm detects this immediately and exits early, returning false because stones 1 equals 1. This highlights a scenario where the frog is unable to even begin its journey, making the output false. To analyze the time complexity of the solution, we start with the outer loop, which iterates through each stone in the array. Since there are n stones, this loop runs n times. Next, we have the inner loop, where the algorithm examines all possible jump sizes stored in a set for the current stone. In the worst case, each stone can have up to n possible jump sizes because each jump is derived from prior steps, and there can be at most one jump size per stone. This means the inner loop also runs n in the worst case. Finally, for each jump size, the algorithm checks 3 potential steps: jump 1, jump, and jump plus 1. This innermost loop is constant and runs 1 per jump size. Combining these factors, we get a worst-case time complexity of n for the outer loop, n for the inner loop, and 1 for the innermost loop, giving us a total time complexity of n *n**1 or n squared. Now, looking at space complexity, the primary factor is the dictionary stone_positions, which maps each stone to a set of jump sizes. In the worst case, every stone could have a set of size proportional to the total number of stones, n. This means the dictionary requires n space for its keys and up to n squared space for the combined size of all sets. Additionally, the algorithm uses a few temporary variables such as stone, jump, and step, which require constant space, or 1. The overall space complexity, therefore, is dominated by the dictionary, leading to n squared in the worst case. When comparing this optimized approach to a brute force solution, the difference is significant. In the brute force solution, the frog might attempt every possible sequence of jumps, resulting in an exponential time complexity of 3 to the power of n, as there are 3 jump options to consider at each step. Additionally, the space complexity would be O, n, due to the recursion stack depth. In contrast, the current solution uses dynamic programming with a dictionary to store intermediate states, reducing the time complexity to O, n squared, and the space complexity to O, n squared, by avoiding redundant computations. For the best, average, and worst case scenarios, the best case occurs when the frog quickly reaches an impossible situation, exiting early in O1 time. On average, the frog explores only a subset of possible jumps, leading to a time complexity somewhere between O, n, and O, n squared, depending on the number of valid paths. In the worst case, the frog explores all possible jump sizes for every stone, resulting in the full O, n squared, time and space complexity. To prove the O, n squared, time complexity mathematically, consider that the algorithm processes each stone and evaluates all possible jump sizes associated with it. Since the number of jump sizes is bounded by the total number of stones, the inner loops are limited to O, n. Combining this with the outer loop over n stones gives an overall time complexity of O, n squared. Similarly, the space complexity is dominated by the dictionary, where each stone can store up to O, n, jump sizes. With n stones, the total storage required is O, n squared. This confirms that both the time and space complexity of the solution are O, n squared, in the worst case, which is a significant improvement over the exponential complexity of the brute force approach. Here, we'll talk about some common mistakes to avoid when solving the frog jump problem. First, it's crucial to handle edge cases properly. For example, if the stones are spaced too far apart at the start, the frog may not have any valid jumps to make. Scenarios like stones equals 0, 1, or 0, 2, 4, 6 should always be tested to ensure your solution doesn't fail on these. Next, relying on an inefficient recursive solution without memoization can lead to exponential time complexity since the same subproblems are solved repeatedly. This is not scalable, especially for larger inputs. Another mistake is assuming that all jumps up to k+1 are valid without verifying the presence of the target stone. Every jump must be validated to ensure the frog can land on an actual stone. Additionally, forgetting to include a base case that checks if the frog has reached the last stone can result in incomplete or incorrect solutions, particularly for recursive or DFS-based approaches. Finally, using an overcomplicated state representation with unnecessary variables or overly complex data structures can make your implementation harder to debug and more error-prone. A clean representation using just the position and the last jump size is typically sufficient and much easier to work with. Now let's dive into some insights you can use during interviews. The key to solving this problem efficiently is recognizing it as a dynamic programming or memoized DFS problem. The optimal solution involves exploring valid jumps systematically while avoiding redundant computations. The frog's movement naturally builds on incremental state transitions based on the last jump size, which allows you to prune invalid states early, making the solution more efficient. During interviews, it's also important to articulate trade-offs. For instance, brute force solutions with exponential time complexity, O2 to the power of n, are impractical for larger inputs, whereas memoization reduces this to O, n squared, by pruning redundant calculations. Additionally, you should highlight the importance of testing edge cases. Examples include stones spaced too far apart, where the frog can't make any valid jumps, or situations where there are only 2 stones, such as 0, 1. These insights demonstrate your ability to analyze and optimize solutions effectively. Let's explore some related problems and alternative approaches. Related problems like LeetCode 70, climbing stairs, introduce basic state transitions in dynamic programming. LeetCode 198, house robber, focuses on optimizing choices using memoization. LeetCode 322, coin change, highlights state transitions based on available options, and LeetCode 139, word break, shares similarities in recursive exploration with memoization. These problems can help build foundational skills for tackling frog jump. Now, considering alternative approaches, recursive backtracking tries all possible jump combinations but suffers from exponential time complexity, O2 to the power of n, due to redundant computations. This approach is only suitable for small inputs. Memoized DFS, on the other hand, dramatically improves efficiency by storing intermediate results, reducing the complexity to O, n squared, and is widely accepted as the standard solution. Lastly, iterative dynamic programming avoids recursion by constructing a DP table, where DP, I, represents the set of jump sizes that can land on stone I. This approach is also O(n) squared, but requires careful initialization and management of the DP table. Finally, let's discuss breadth-first search, or BFS, as another viable approach. BFS frames the problem as a graph traversal, where each state is represented as a node, defined by the current position of the frog and the size of the last jump. This approach systematically explores all valid states level by level, ensuring that no state is revisited unnecessarily. Although BFS is efficient in avoiding redundant computations, its implementation can be more complex compared to dynamic programming. You need to manage a queue and ensure that each state is processed correctly, which can introduce additional overhead. Nonetheless, BFS is a powerful alternative if implemented cleanly, particularly when you want to explore the problem from a graph-theoretic perspective. Great job! We successfully solved the frog jump problem using a dynamic programming approach with a hash map. Remember, mastering state-based problems like this can significantly improve your algorithmic thinking. Thanks for tuning in, and don't forget to like, subscribe, and keep practicing. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!